Okay, so I think we can start. So I was asked to tell you today about color centers. So this is Color Centers 101. And to be honest, I don't really know much about color centers, so I'll be talking mostly about NVs. I will try to put this in the context of color centers in general towards the end, and to maybe try to give you also a feeling as to why, after people have found this really exciting, useful system like the NV, why it's still worthwhile looking for other useful color centers that we would like to study and potentially use for quantum applications. So this is the kind of like short intro slide for those of you who are not in the NV business. Just to give you a motivation, we're talking about localized atomic defects within solid structures, in this case diamond. So this is kind of a little cartoon of a diamond lattice with an NV defect in it. And, people coming from atomic physics or cold atoms or ions or anything like that would potentially appreciate the fact that having such a localized system, which essentially has an atomic structure, not precisely, but looks like an atom, that we can address and manipulate without having to do any trapping or to use any vacuums or cryogenics or whatever, is potentially attractive and useful for practical applications. So we have this solid state system hosting an atomic-like quantum system. By quantum, I will pretty much always or almost always refer to the ground state spin degree of freedom, which is quantum in the sense that it has a relatively long coherence time on the scale of hundreds of microseconds at room temperature, and that's why we can think about it as a quantum spin or a quantum system. And in addition to these nice properties, it's also optically accessible. So these are color centers in the sense that they couple to light, they fluoresce, and we can use this optical accuracy both for initializing and reading out the quantum state of the system, which is extremely useful for many types of applications. So trying to realize or to utilize these types of systems gives us a nice platform for various types of quantum technologies and also quantum science that I might mention briefly during this talk. And this has stopped working. So everything is stuck. It's just stuck. Okay, so following this short introduction, the plan for this talk is to give you some basics, and I'll start by talking about the NV system. I'll try to give you some basic properties, and then I'll talk a little bit more about the spin degree of freedom and the optical coupling. After going through these kind of fundamental properties of NVs, as I promised, I'll also mention some other interesting color centers, both in diamond and in other materials that have been and are being studied and have, potential advantages or kind of interesting properties compared to NVs. So let's start. As I mentioned, the NV is a localized defect within a diamond crystal. So the blue atoms here will depict carbon atoms of the diamond lattice. And the NV is a substitutional nitrogen replacing one of these carbon atoms with a nearby carbon atom missing. And that's a vacancy. That's why we call this the NV. And this combination produces the set of properties and the set of physical characteristics that I'll describe in a second, which makes it an interesting system for us to discuss. I just want to mention briefly, without going into too many details, that we don't usually use such nice diamonds in the lab. We usually have pristine diamond plates that are in almost all cases synthetic diamond, lab grown, mostly using CVD, which is chemical vapor deposition. There are also diamonds that are created using high pressure, high temperature, or HPHT processes. And it's important maybe to note that this technology of growing and creating synthetic diamond has really improved over the past, say, 20 years or so, and is still being developed to the point where people know how to grow very well-controlled diamond substrates, controlled in the sense that they can have relatively low strain, they could have somehow controlled defect concentrations, usually nitrogen, but not only, and can even be grown with isotopically enriched content. So the carbon atoms that appear in the diamond lattice are mostly naturally carbon-12. They have no nuclear spin, which is good for us. Why? I'll tell you a little bit later. But 1% naturally of these carbon atoms are carbon-13 isotopes that have a nuclear spin, and therefore they can kind of couple to our NV, not necessarily in a good way. So people also know how to grow carbon-12 enriched diamond these days that can be up to like 5 nines or something like that, carbon-12, in such a way that would significantly suppress any potential effects of these C13 isotopes. And in CVD, for example, this is mostly done by taking the forming gas in this process, the methane, and using isotopically enriched methane that has already in it this reduced C13 content. It's actually very hard to do this isotopical enrichment, and these little bottles of methane are super expensive. But still, that is something that can be done. One other thing that I wanted to mention briefly before going on is that the control that people have on this diamond growing processes allows you to some extent control the content or the concentration of defects, specifically defects you're interested in, let's say NVs, within the growth process. So people can create diamond plates that have negligible NV content, that have high NV content. People know how to grow layers of these things. So there's various control schemes that can be applied in the growth process to create a desired substrate in terms of the defect profile. One can also use additional techniques. So for example, many of us take pure diamond plates that have negligible defect content and then implant them post-growth with the desired ions. For NVs, these would be nitrogen ions. So one can actually shoot nitrogen ions into the sample to create NVs at some given concentration and some given depth. And then there are additional processes as to how to make sure that you have a good conversion from the nitrogens that you've shot into the diamond into the NVs that you actually want. So usually we don't want the Ns themselves, we want the NVs. And there are additional processes that can be done, including electron irradiation and sometimes even proton or carbon implantation. There's a nice poster about this that I saw yesterday. So there's various processes that are involved in creating our samples, our substrates, that include both the growth process and the post-processing in terms of implantation, irradiation, annealing, and so on, that I'll not go into the details of unless you want me to. Okay, so now we have our sample. We have maybe NVs in it. What are these NVs? So the NVs are these nitrogen vacancy defects, and they can appear in different charge states. There's the neutral NV, NV0, the negatively charged, NV minus, which is the one that we like. It has the properties that we can use. And maybe there's also an NV plus, which is kind of elusive. But if you look at the kind of the rough energy level diagram of NV minus and NV0, you can see that we have an electronic excitation at almost 2 eV, 637 nanometers for the NV minus, and 575 nanometers for the NV0. If you look at the, and I'll try not to go into too many details about this, but if you really look at the molecular orbitals and try to build up the structure of this tetragonal symmetry, C3V symmetry of the NV, you can sort of realize that the NV minus has a spin triplet, but in orbital singlet ground state, while the NV0 has this singlet ground state. And the NV also has a pair of singlet states here that have an energy splitting of about 1042 nanometers. I think first measured by DEMA here at Mainz, was measured at Berkeley, which is important. This transition and these singlet states are important for some of the photodynamics and some of the emission properties of these NV minus systems. Okay, so these are the electronic transitions that are related to exciting, say, this structure into the excited state. If we look first at the ground state, which is this spin triplet, we can see that it has, this is the Hamiltonian of the ground state manifold of the NV minus. I'll be focusing mostly on the NV minus, which is what we're mostly using. So the spin triplet ground state of the NV minus has a zero field splitting, this spin splitting, usually called D, on the scale of 2.87 gigahertz, which splits the MS equals 0 spin state from the plus minus 1 states. And in addition to that, it has a hyperfine coupling to the nitrogen nuclear spin associated with that NV. And that hyperfine coupling then splits the states between the within the plus minus 1 manifold between the zero. Okay, sorry. The nitrogen is mostly nitrogen 14, a nitrogen 14 isotope with a nuclear spin of 1. So it has 3 sublevels, which you can see the splitting of here. There's also sometimes you can find N15 isotopes with a spin half, and there you'll see a double splitting and not a triple splitting here. When we're talking about the the A's here are the hyperfine coupling coefficients for the parallel and perpendicular terms. When we're talking about the N14, the spin 1, we also have a quadrupolar splitting of the nuclear spins, which you can see both in the ground state and in the excited state, and the 0 and plus minus 1 states. Okay. Now, if I go over to the excited state, things become a little bit more complicated, actually annoyingly so. If you look at the excited state structure, we actually have an orbital doublet with a spin triplet. So how many states? Yes, someone said 6. So there's 6 states, and they're controlled by this Hamiltonian. I won't go into all the details. Actually, I just wanted to mention that a lot of what I'm showing you here about the basic structure of these NVs is taken from a nice paper by Doherty, Hollenberg, and others from 2013. So it's kind of a nice review. But I'm not really fond of the symbols they use. So these sigmas are the orbital degrees of freedom, and the S's are the spin. But in any case, it includes again, an excited state splitting, zero field splitting, which is approximately 1.4 gigahertz. And then we have, in addition to that, the spin orbit couplings and the and all the different combinations of these perpendicular splittings as well. That makes things relatively complicated, but in principle, you see these different states. Here we have degenerate doublets, so total 6 states. However, if you go to room temperature, things become nicer. Why? I don't know. So at room temperature, the orbitals, remember I mentioned that we have two orbitals and a spin triplet, so 3 degrees, three spin sublevels. The orbitals average out. So they couple efficiently through phononic couplings in the excited state in a way that preserves the spin structure. And effectively, one can write a room temperature Hamiltonian, which only includes these spin degrees of freedom. Here again, similar to the ground state Hamiltonian I showed you before, we have the zero field splitting, the hyperfine coupling with the nuclear spins, and again, a quadrupolar splitting. We can also write the coupling term in the Hamiltonian if we add any kind of additional fields. These could be electric fields, magnetic fields, and strain. All of these, of course, couple into these states. So how do we go from this kind of actual structure into this relatively simplified scenario? I don't know, but somebody knows. And this is kind of a nice measurement and maybe a nice picture of what actually happens here. So if you remember, I showed you this this kind of low temperature structure with these six states, the two orbitals and the spin degrees of freedom. When you heat things up and you go into room temperature, all of these orbitals mix together and we retain the spin structure only in the excited state, and that is what we will mostly use. This is the scenario that we'll encounter at room temperature, and it's an extremely useful and simplified scenario that allows us to, for example, retain the spin degree of freedom in most optical cycles. If you induce that higher strain into the system, you can actually reach a point where you're splitting these orbitals very nicely, as opposed to the low strain, low temperature scenario, and you can really see the separation between these two orbitals and the spin degrees of freedom, spin triplet in each one.
That high strain energy.
So this is at low temperature, because otherwise you'll be very, you need really high strain to be able to separate it out in this way at room temperature. So this is some low temperature picture. I do want to point out this nice result here. These are actually simulations and measurements that were done in Patrick Malatinsky's lab. This is the reference, and what this shows, this is actually a color map of fluorescence intensity, right? So I haven't really said it yet clearly, but this NV minus system, when you excite it to the excited state, it fluoresces. It's optically active and fluoresces in red. And this is a color map of the fluorescence intensity as a function of temperature on the x-axis and of a magnetic field on the y-axis. And you see various interesting features that I will not necessarily go into completely, but I would like to point out to you that this is kind of a low strain scenario. So assuming an NV that's low strain, but if you look at the high temperature region, this basically room temperature region, you can see that fluorescence is pretty constant, except 2 drops at 2 points that are associated with the zero field splitting. So these are called level anticrossings. The low one here at approximately 50 millitesla is the excited state level anticrossing associated with the D in the excited state. And the other one here at about 100 millitesla is associated with the ground state level anticrossing. When you mix these up, fluorescence is reduced. You're starting to mix the spin states, you get reduced fluorescence. So this is relatively easy to explain. When you go to low temperature, you see that things become more complicated. You get additional fluorescence drops that are associated with the level structure that you see here, all kinds of mixings that occur as a function of magnetic field in this orbital structure. And then everything kind of disappears, mixes up phononically at approximately 50 Kelvin. And above that, at some point, you just get these things to reappear. So without going into too many details, you can read more here. We can actually we can sort of understand these dynamics from these types of Hamiltonian structures. And actually, I don't know if you can read it from back there. These are simulations, and this is the actual experiment, so they fit rather well. But to tell you exactly what's happening in these transitions is not so trivial, and I think it's an interesting question for various types of fundamental issues, but also for applications. Okay? Good. So, yes, sorry.
Sorry, don't you have any contribution like surrounding carbon atoms to the Hamiltonian?
Good. So,
Okay.
So let me see if I understand what you're saying. Why doesn't the interaction Hamiltonian include, I don't know, some magnetic coupling to other defects or to other isotopes? So it definitely could be included. Usually we don't do this because we're interested in kind of separating out our quantum system of interest from the environment that surrounds it. But let me come back to your question in a little bit. I'll show you what I do, and then you'll say if you're happy or not. Other questions? Yes.
So like in the y-axis about like 100, 200 and 300 for like 0 to 50 Kelvin we can see a like straight PL drop like what?
So these suppressed fluorescence regions or points are associated with the different mixings that occur between these orbitals that are separated at low temperature, but you don't see them. They all get mixed up to this single excited level anticrossing at high temperature. So these things, and they will move when you have high strain or low strain, but the values of these magnetic fields which mix the different spin levels are associated with the splitting that's given from the excited state. Okay, so maybe the important takeaway message is that what I showed you earlier, the structure of the excited state is not trivial. These are 6 levels, 2 orbitals, and 3 spin substates. And they will, of course, depend on the basic parameters like the zero field splitting and so on, but also on strain and other external fields that might be around. And they have to be taken into account when you're thinking about the dynamics within the excited state at low temperature. At high temperature, phonons that are extremely fast and efficient in mixing these orbital degrees of freedom essentially get rid of all of these dynamics for us in a nice way that retains the spin degree of freedom that we can use. So we tend to think about, people working at room temperature with NVs tend to think about this nice excited state structure, but sometimes if you're going to a lower temperature or experience very large strain, you have to keep that in mind. Yeah.
I have a question about the high string and low string picture. For example, of the high string, the +1 and -1 levels are splitting into the 4 levels, right? But the marker is still the +1 and -1. So I'm wondering, it is split to 8 levels or 4 levels?
Here?
Yes.
So are you talking about these kind of like dotted lines that show the splittings?
Yes.
Yeah, so what's actually happening, so you always have 6 levels. I mean, that's what you have in there. An orbital doublet and a spin triplet, right? And you can see this here. These are degenerate at 0 strain, so you can see 6 levels. The reason why you see only 3 here is because it's hidden in there that the orbitals are completely mixed. So each one of these spin states is a combination of both orbitals that you just don't see, they average out. So then these dashed lines, which split them at high strain, essentially try to say that the hidden orbitals of each one of these spin sublevels get split. So these are X and Y splittings because of high strain. So you get all of the spin sublevels, 0 plus minus 1, 0 plus minus 1, and the 2 orbitals. But it's always 6 levels. Other questions? Excellent. Thanks. So before I stop talking about these optical couplings for a while, let me just maybe mention the fluorescence spectrum of these NVs. Here I'm showing a fluorescence spectrum both of NV0, which I remind you has this transition at 575 nanometers, and then kind of a phonon sideband. We usually call these main transitions the ZPL, the zero phonon line, because this is the line that describes emission without an additional phonon coming out. And the NV minus has this ZPL at 637 nanometers, again with this sideband that comes with it. Now, as I just mentioned, we have a relatively broad sideband for the NV minus. It goes up to almost 800 nanometers. It's pretty large. And the zero phonon line is weak. Now, I have a silly question. I tell you that the zero phonon line is weak. It doesn't look like it. Looks pretty strong. Why? Let me just say, weak is, it's approximately 3 or 4% of the fluorescence emission when you integrate over the entire, side. So this is a measurement, again, taken from the Doherty review that was done at low temperature. And you see this, these ZPLs. I'll just mention, I don't want to waste your time. It's it's an artifact of the spectrum analyzer. They because it's kind of scanning over these regions, you see this is a very strong peak, but it's really very weak.
It just rather folks all things about, I know.
That's true. And it's very narrow. So this is actually one of the downsides of the NV as a system that's optically coupled, because the coherent coupling, the zero phonon line, coherent in the sense that it does not involve also coupling with phonons or other stuff that we don't like from the lattice, is so weak. The reason it's so weak is because of a small Debye-Waller factor, which essentially, this Debye-Waller factor essentially tells us how many inelastic scatterings we get when we, scatter light. Originally, I think this was done for X-rays in crystals, but it tells us how much elastic scattering we get as opposed to inelastic scattering. So all these phonons are the dominant factor for NVs, and then the Debye-Waller factor is relatively small.
Sorry, Nir, are you saying that this picture is inaccurate, or do you say that so that the line should actually be smaller?
So it's essentially similar to what Elke said. This looks very large because of the fact that when you look on the optical spectrum analyzer, you're looking at a very, very narrow region, but it has like these jumps. So it gives you like a very nice, strong peak, but when you integrate, you get a few boosts.
Okay.
It's not a long.
But this is also a huge ZPL peak for spectra, no? I've seen smaller ones.
Not the side that matters, Anyway, so I do want you to keep in mind that this is one of the downsides of NVs, especially when you're trying to think about these coherent couplings. Maybe I don't know, since we're kind of talking about this, I like these combinations of names. When you look at this emission spectra, how can you what's maybe the simplest approximation or the simplest model for figuring out what would this emission spectrum look like? This is something that's called Frank Condon. I don't know if any of you are familiar with this. It's basically sort of like a kind of like a Born-Oppenheimer approximation where you're saying everything looks like harmonic oscillators, because we don't know anything else. And then when you excite, the electron moves, but the nucleus, the nuclear spin doesn't have time to move. So it's fixed. And then you just calculate, well, Frank and Condon calculated, you can see what the overlaps are of these different harmonic oscillator wave functions, and you get the strength of the coupling to each one of these levels. So I don't know, look it up. It's very useful. But this type of approximation tells you something nice, that if this is the emission spectrum of your system, it's true for NVs, but it's true for almost all atomic solid state systems. What would the absorption spectrum look like? Like a mirror image. So it's approximately, it's not exact, but it's a very good approximation. It will look exactly like a mirror image taken to the lower wavelength part of the graph. So you'll get like this bump of absorption. Where is the bump mostly maximal? Anybody working with NVs knows? Yeah, so around green. Yeah, so maybe I don't.
Can you just take the microphone? A bit of microphone discipline, please.
Microphone discipline. I like it. So yeah. So if you guys are not familiar, look it up. It's good to know these things. So this was first done by Frank and Condon. Frank is a Nobel laureate. What did he get his Nobel Prize for? Ready? He did it with someone else in an experiment that you all did in your undergrads, I think. Didn't? Huh?
They
Not you guys. Anybody ever done the Frank Hertz experiment? You know, where they first realized that there were atomic levels in mercury, I think, originally. So Frank and Hertz got the Nobel Prize for this. James Frank then did other things also. Never mind, a little bit of history. So I also wanted to mention...
Yeah, maybe one remark. Maybe you should say what phonons are in this case.
Ooh, okay.
This might... For the molecule, it's clear, right? But for the solid?
So I'm going to ask you the question in a second. So this is a good question and a difficult one because, okay, what are we talking? What do we mean about this phonon sideband? So it means that once you have this emission, right? We're in the excited state. We're emitting light. So along with this light, we can also emit phonons. What are these phonons? So in principle, phonons are these lattice vibrations. What are the actual lattice vibrations? What are the actual phonon modes that are coupled, in this case, to the NV defect? It's not so trivial. There are bulk phonon modes that are kind of like the standard modes of the Bose-Diamond crystal, but there are also localized phonon modes that you can actually see very well separated out here that are strongly coupled to this specific defect, and how these phonon modes actually look like and how they behave is not so trivial. Maybe later you can ask LP about this. But it's a very interesting point, and it's actually very important because if you think about it, what we were saying a minute ago about the fact that this excited state level structure gets completely mixed by the phonons, but in a super nice way that retains the spin degrees of freedom, that's not so trivial, right? So it comes about from the symmetry of this defect and of the phonon that strongly mix it. So I think it's a very interesting point. I also just wanted to mention, and maybe I'll mention this also a little bit later on, if we are talking about optical coupling and coherent versus incoherent optical emission, it's very interesting to look at the line width and also the line center of the emitted fluorescence from the NV. This is, of course, all done at low temperature because at high temperature, everything is washed out by these phononic couplings. And we usually excite our NV in green when we're working at room temperature. But of course, the coherent coupling, the low temperature coupling, if you'd like to do this coherently, is in red. This is 637 nanometers. And this is an experiment measuring the resonance position of the NV minus emission as a function of time, so that the y-axis here is time, and the color is the strength of the emission. And you can see that this thing moves around. When you just excite it with red, it doesn't move too much, about a gigahertz or two over, many, many repetitions. But if you use also green, it just jumps around like crazy. Why does it jump around like crazy? No, never mind. I'll tell you later. Think about it. Okay, yeah. This was, I don't remember exactly, but around 5K. Could have been a little bit more or a little bit less. I don't remember. It's from this paper from, oh God, bad with names. Sorry, but it's from this paper from Berlin. Okay, so I think I want to now switch gears. And after I've introduced to you the electronic structure of the NV minus, both ground and excited state, let me focus on the simple stuff. Room temperature, ground state, spin degree of freedom. Okay? So as I mentioned before, the ground state has an orbital singlet, which is great, and a spin triplet. And the spin triplet, these three sublevels, 0 and plus minus 1, are what we always think about when we think about the NV as a quantum system, as a quantum spin, as a qubit, as a sensor. Okay? So these are the degrees of freedom that we like. And as we've discussed, even though it has a zero phonon, an optical transition, a zero phonon line at 637 nanometers, because of this Frank Condon thing, the maximal absorption occurs around green. So we can excite it with green. It doesn't excite directly to the excited state. It goes through phonons because it's, in that absorption band. But it's efficiently exciting the NV so that it can fluoresce, and then it will fluoresce with this broad red fluorescence, 640 to 800 nanometers, which we can measure. So we can measure this fluorescence and get information. How do we get information? If you remember the pair of singlet states that we have here, the excited state can decay through them back to the ground state, but in a spin non-conserving manner. The optical excitation and emission conserve spin. The excited state structure, if you remember, mixes the orbitals but retains the spin degree of freedom, the separation of spin. So if we excite from 0, it emits back to 0, and if we excite from 1, it emits back to 1. The non-radiated transition through the singlet states are determined by spin-orbit coupling, and they spin mix. And then we can get relaxation, mostly from the plus minus 1 spin states into the singlet and then back somewhere. So what happens is that we get fluorescence from all spin sublevels, but more from 0, which does not, or almost does not undergo this non-radiative relaxation. And we get less fluorescence which can decay through this channel. So just by measuring how much fluorescence we get from the system, we can tell if we were at 0 or plus minus. And this is our optical readout of the spin degree of freedom, or the quantum degree of freedom of the NV. In addition to that, the fact that 0 stays at 0 and plus minus 1 has a probability of relaxing back to 0 allows us to initialize this spin degree of freedom of the NV just by shining light on it for enough time. And this is just an example of the fluorescence we measure out of the NV as a function of time, where we turn on this green light. So you can see that, the two colors, blue and red, are for the plus minus 1 and 0 spin sublevels. So you can see that because plus minus 1 can decay non-radiatively, we get less light in a window of approximately 200 or 300 nanoseconds. So by measuring how much red light came out of the system, we can know if we were at 0 or at 1 in this time window. And after enough time, usually approximately a microsecond, they both kind of converge together when we've already pumped the system into MS equals 0. Okay, so we can just use this to initialize and read out the spin state of the system. I'll just mention that the time scale here, where we can measure this, where we can perform spin readout, is determined by the lifetime of the singlet state, which again is usually around 300 nanoseconds. Yeah.
Thank you. Okay. The nature of these two curve in that particular region, like it will increase, both increases for initial time, and like it also like accumulate, like saturate in the same level after a certain amount of time, but in between that time there's like for like ±1 it will decay and then again increase. So that why we
Why do we see these types of dynamics? So that's a very good question. It's not so trivial, but it's related to the just the dynamics of this photoexcitation process. So if you can actually put in the numbers, right, and you see what your excitation rate is, and then the rate for relaxation here and the rate for relaxation there, you just calculate, you see this exact dynamics. So this initial rise and this initial drop are associated with transient dynamics. So it starts starting from the ground state and then exciting and starting to fluoresce. And then eventually it goes into kind of like a more standard kind of relaxation process. So you can, as a nice exercise, you can just run a rate equation system of, I don't know, you need at least 5, but maybe a bit more levels, and you'll see this exact dynamics. Okay? Other questions? Good. So this is the basic idea of the optical coupling, and I'll just mention that if you remember the splitting here between the 0 and ±1 states in the ground state, this zero field splitting that's associated with the spin-spin coupling of this of the electrons in this defect in the ground state is approximately 2.87 gigahertz. So it's a microwave regime that we can apply. You know, we can apply microwaves, drive this coherently, so it's a very convenient energy scale to work with and to create coherent manipulation. Yeah.
Could you please just walk us through what's happening in the non-radiative decay process?
Here? Yeah. These wiggly yellow lines basically represent phonon-assisted relaxation from the excited state to this singlet state. Now, this phonon transition is realized through spin-orbit coupling. Okay, so the spin-orbit coupling is associated with orbital degrees of freedom that are then coupled to phonons, and they create this relaxation path. Now, for a very non-trivial reason, it's very difficult to calculate from first principles, but this coupling is significant for the ±1 spin states, but not so for 0. So you get this relaxation for ±1 and almost nothing for 0. And that, sorry, yeah?
That would have been my follow-up. Like, why does it not happen for the zeros?
Yes, so I cannot answer that in any reasonable way. It's something that we definitely see experimentally, but to really calculate this, aside from saying things like, you know, this is suppressed through the phonon symmetries versus the symmetries of the defect, and the way the 0 and ±1 states are coupled to the orbital degrees of freedom. Aside from that, I can't really say anything, and it's very difficult to calculate this a priori. In addition to that, until 10 years ago, nobody knew what the energy splitting here was. This was measured through IR absorption, I think, in Dima's group. So we know that this is 1042 nanometers, and this transition actually so 1042 is IR light, but it's also strongly phonon coupled. So the relaxation here, you can see IR light coming out, but very little, because there's a competition between phonon-assisted relaxation versus optical radiative relaxation. So the light coming out of here is relatively weak. The lifetime of this excited state, because of the phononic coupling, is short, less than a nanosecond, probably about 100 picoseconds. Maybe some people here have measured it, I don't know. And then the ground state is metastable in the sense that it has a lifetime of approximately, like I said before, 300 nanoseconds, then relaxing non-radiatively anywhere. Again, it's kind of like spin-orbit coupling that allows you to relax to different spin states. But to give you a kind of a more precise answer, I cannot. Sorry.
Thanks so much.
Other questions? Okay. So the experimental system is essentially an optical microscope. This is just a picture of one of our systems where we have an inverted microscope with an objective here. The diamond is sitting here. On top, there's just a static magnet that we use to apply magnetic fields to the sample. And the whole thing is sitting on top of a microwave antenna with, cables coming out that allow us to drive this spin transition. So in principle, this is a relatively simple experimental setup if you're thinking about, this room temperature spin degree of freedom type experiments. And by doing microscopy, we can scan the system around, this is a sample with a low concentration of NVs, so we can find these separated fluorescent spots, and we can focus on one of them. And maybe the takeaway I'd like you to remember from this is that it looks trivial, but we're looking at a spin. I mean, we're interested in spin. People have been looking at spins for, 100 years with various NMR type techniques. The fact that we can address this spin optically and do the initialization and readout gives us an advantage, right? So we can look at one. It's extremely difficult to localize, magnetic or microwave fields or RF fields in a way that allows you to get this spatial resolution. So the optical coupling here, even at room temperature, is extremely useful. And now we can go back and do what people in NMR have done forever and ever. And we can start looking at the spin degree of freedom of this defect. The simplest experiment, by the way, I'm saying NMR all the time, but this is an electronic spin. I'll mention the nuclear spin of the nitrogen a little bit later on, but we're focused on the electronic spin, so this is more like EPR, electron paramagnetic resonance. And the simplest CW experiment is called sometimes ESR, electron spin resonance. Since we're measuring it optically, in our community, we tend to call it ODMR, optically detected magnetic resonance. But in principle, the experiment says, let's shine green light on the system, measure the fluorescence, the red light that comes out, right, continuously. We don't change anything. We just shine green light, measure red light. But we now apply also a microwave field and scan its frequency. And by scanning its frequency, we can try to couple the 0 and ±1 states directly through the microwave coupling and see how the fluorescence changes. So this is the change in fluorescence. And we can see that when we hit the resonance with our microwave field, we're efficiently driving 0 ±1, so we get less fluorescence. And this is a resonance experiment. We can see this nice resonant line shape, and we can find the this zero field splitting, this transition energy at 2.87 gigahz. We can, of course, do this with at zero field, like I showed before, but we can also do it at a finite field, finite magnetic field. And this magnetic field splits the ±1 spin sublevels through linear Zeeman effect. And this splitting then shows up in this ODMR experiment through a split in the resonant frequencies of the transition from 0 to -1 versus the transition from 0 to +1. Okay, simple. This is the simplest magnetic measurement, DC magnetic measurement scheme. And one can use this, for example, as in a microscopy setup, as a magnetic microscope. So you can use it actually to image magnetic fields just by looking at the ODMR, this structure. On a diamond sample, this is a diamond plate with a lot of NVs on the top, right? Close to the top. And we place something that we want to measure on the diamond. So basically we can image the fluorescence from this top layer of NVs onto a camera. And then it images each pixel of this image is light, right? It's fluorescence that we collected on our camera, but we repeat each one of these measurements when we scan the microwave field, like in this ODMR I showed you before. So we find the resonances in each pixel and translate them. Here, the color map, you cannot see this, I apologize, is magnetic field. Okay, and you can do this for various 2D magnets. You can do this for, I don't know, paleomagnetometry. You can do NMR with this. You can do various. Okay, so the simplest CW experiment already gives you a nice tool for doing magnetic sensing. And because of the optical coupling, it can be translated into magnetic microscopy in various scenarios that could even be useful or interesting. Okay? But that's too simple. So let's move on to pulsed experiments. Once we've identified the resonance of our transition, we can park our microwave at that frequency and then run a pulsed experiment where we first initialize our spin to 0 using green light. Then we apply a pulse of microwaves at that frequency, but we vary the duration of that microwave pulse. And then again, we apply green light just to detect, to measure the spin state. And the experiment looks like this. We have the pulse, the length of the microwave pulse on the x-axis, and the measured normalized fluorescence on the y-axis, and we see oscillations. What did these oscillations mean? It means that we've started from, say, 0, say, because we've initialized it with green light, but then this microwave pulse rotates it from 0 to, say, 1, back to 0, and so on and so on. So this is, stay 0, this is 1, 0, 1, 0, 1, so on and so on. And this is very well known. This is called Rabi oscillations. This is I. Rabi, who got the Nobel Prize for this. And this is also Rabi, with who? Another history lesson. Both of these are also Nobel Prize laureates in physics.
Ernest Lawrence, one of them.
Good. Who said Lawrence? You can't see. So this is Lawrence, and the little guy is Fermi. What did Lawrence get the Nobel Prize for? Okay, look it up. He invented the cyclotron, which you don't know anymore because it's old, but it's the father of the synchrotron, which you probably all know. So he got the Nobel Prize for that. Anyway, they're probably friends. So this idea of getting this coherent control, coherent driving of these things might look trivial to you guys because you're super smart, but it was very novel back then in like the 30s, maybe 40s, 30s, when Rabi got into this. Because if you remember, people were just after Stern-Gerlach experiments, they realized there is something like spin. They wanted to see how they can control that. And those were the first initial steps towards NMR. Okay, and Rabi, when he died in like 89, wasn't very healthy anymore. He went like probably 1988 or something to get an MRI measurement. And he said, I never believed it would come up to this. So, sometimes when you do things that seem not necessarily practical, you never know. So keep doing whatever it is you're doing. But as you all know, this is a nice technique, but there's also maybe a better way of interrogating spin systems, especially for sensing. And that's due to Norman Ramsey. The idea, by the way, he was Rabi's student. So he was seeing what Rabi's doing. He said, that's crap, let's do something better. So the idea was to, again, initialize and read out. This is the green light. But instead of driving your system with this pulse of various lengths, right, this Rabi driving, he said, let's do just a very short pulse. They call it a pi/2 pulse because if you rotate your spin from 0 to 1, that's like 180 degrees. So pi/2 pulse rotates it only to the middle. What's the middle between 0 and 1? And a superposition of 0 and 1. And then you just don't do anything. It's very efficient. You don't do anything. You wait, and then you measure. So you can measure with another pi/2. You can measure in NMR just with looking at the precession. But then you just measure. In the NVs, we apply another pi/2. And then we see, basically, we can really probe the precession of the spin in this XY plane of the Bloch sphere as a function of this time, which is called the free precession time. And we can see these oscillations that decay. And this is essentially interferometry, right? We're creating an initial superposition and measuring the phase over time, the phase evolution over time. And this is maybe the most sensitive way of measuring phase. Maybe, I don't know, this is how we define the second. So it's really good. He called it the separated oscillatory fields technique or something like that. It's easier to say Ramsey interferometry. And he got the Nobel Prize for this as well in '89, I think. And this is also Ramsey when he was younger. What is he doing here? Yes? He is signing something circa 44, 45. He's signing the atomic bomb, the Fataboy. So he was also part of the Manhattan Project during those days. And we use this technique a lot. In NMR, it's called free induction decay. Sometimes it's called Ramsey interferometry, but it's the same thing. What this tells us, it tells us how long the phase of our spin, of our system, of our NV, can process coherently before, everything dies out. This time for losing the phase of our system, for dephasing, is in NMR usually called T2 star. Okay, so we can measure the T2 star time of our system using this technique. By the way, if I initialize my spin and then watch it decay, I'd expect to see a decay curve. Why do I see oscillations that have an envelope that decays, but I see oscillations? This is an actual measurement. Probably some of you have done this as well. But why do we see oscillations? Because
of a detuning.
Perfect. So actually our measurement, because it includes two phase coherent pi/2 pulses, it's like we're measuring in the rotating frame. Okay, like you saw in Arnie's beautiful simulation yesterday. But if we're detuned somehow, then we have a rotation that we don't see, that you sent to the rotating frame, and this is the oscillation that we see here. So one can actually perform this experiment on resonance in the rotating frame. You will not see any oscillations. You will just see decay. Okay, and then we can extract T2 star or whatever. I don't have an exercise session today, so I'm just putting this up there. And I was wondering, how should we measure T2 star? So, you have this plot. You can fit it to a decaying cosine or something and measure and extract the T2 star. But what's the best way to do this? It's actually a silly question. I asked this during one of my talks that I gave in Bar-Ilan University, and someone actually listened, so they wrote a paper and with an answer. I'll just ask you, what do you think? When you do, some of you do like these Ramsey experiments, you want to measure T2 star. The question is, what times should you choose to measure? I mean, you have this kind of like decay plot. You have, I don't know, you have this amount of time until lunch or whatever. You want to go home at some point. What would be the best time points to choose to measure this? Do you have a guess? How do you choose these time points optimally? Someone has a guess.
Pick just the peaks, so you get the decay envelope.
No, but let me make the question. I mean, there's a complication, of course, because when you have detuning, the decay is not just a simple exponent. It has this cosine thing underneath. But even with the cosine thing underneath, you don't want to, that's not the optimal strategy. But even assume that you didn't have, everything is on resonance. You don't have these oscillations, you just see an exponential decay.
What do we know? We must know something to start, no?
I wish they knew something. Let's say you're me, you don't know anything. Okay, I'll leave you with the question. You can find the answer here. The answer is at 1 point. But you can really calculate this. It's a fun exercise. So let me go on to the question before. This NV, this nice quantum spin system, is not is not a trapped ion or is not, a neutral atom. It's sitting inside a solid structure with crap around it, right? So we sometimes have to take that into account. And in this little picture, we have the NV, but in addition to that, I put in common noise sources, common environments that our NV encounters. One of them are these C13 isotopes that I mentioned at the beginning. They have a nuclear spin of 1/2, and they couple to the NV. We need to somehow maybe take that into account. But also, usually samples that have NVs in them tend to also have nitrogens without Vs. So they have just these substitutional nitrogens, which are a different defect with an electronic spin that can also couple to our NV and potentially cause problems. So when we talk about, for example, like I showed you this Ramsey experiment before, when we see this dephasing, nobody asked where it comes from because you probably all know the answer, but it comes from the environment, from noises around our system that we cannot really account for precisely. And when we average everything out, it looks like a decay. So these types of impurities and any other noise source in our system can couple to the NV spin degree of freedom and create relaxation, decoherence, and so on. So this is, again, well known from NMR. Someone once told me, in condensed matter, everything you do has been done 70 years ago in Soviet, JT, whatever. So in NMR, it's the same. Everything you do with IPs was done in NMR by Robbie 7 years ago. So this time it was done by Han. And Han's idea was to take Ramsey's experiment. Sorry, question.
I'm just wondering, you mentioned on the last slide, you mentioned different things that could go wrong, either an additional nitrogen or a C13. The rest of the diamond is C12, right?
In a natural system, 99% is C12 and 1% is C13.
And if you remove 2 carbon to place the NV there, the one that you actually want, where does the carbon go? Does it leave, or is it also perhaps a problem if it's just floating around?
Yeah, so it's a good question. In most cases, these carbons, you created a vacancy here. In most cases, they somehow diffuse to the surface and go away. In the growth process, this definitely happens. And also in the creation process of diamonds, there's always vacancies inside and always other things in there as well. So they just fuse away in a very short time scale. For us to get the vacancies to kind of relax the structure and not create deformations, which also happen, we tend to anneal our samples, basically heat them up in vacuum at around 1,000, 1,200 C degrees to help this thing relax. But there are always things that are still in there. Carbons that are not in the right place, all kinds of grain boundaries or things like that. There's always stuff. We try to relax the diamond as much as we can, but it's never perfect. Other questions? But maybe it's important to note that people know these days how to grow and create diamond samples that are very, very nice and pure, but nothing's perfect. Not diamond and not any other material. So there's always going to be something. I'm perfect, yes. So I wanted to show you, this is from Wikipedia, that Hahn in 1950 realized that Ramsey's experiment is extremely nice and it measures this dephasing, but this dephasing is in many cases dominated by just inhomogeneities in your system, just random environment structure around each spin, that when you average out your signal, you just see decay that is not necessarily the real decay, because things are static. It's just static inhomogeneities. It's like an unknown DC field that moves your resonance around without you knowing it. And Hahn, who was known as the magician of NMR, invented a very nice trick called the Hahn echo, where he just added to this is 90 degrees is like a pi over 2 poles. So between the 2 pi over 2 pulses of Ramsey, he added a pi pulse, which just flips you around to the other side. And by doing that, you can actually cancel out, as you can see from this nice animation that I would never have been able to do myself. You can see how that causes this dephasing, this spread of the spin to refocus back after the exact same time, and we get our sort of like our coherence back. Because this process of this T2 star process, this dephasing process, is not a real loss of information. It's just information that we don't know, but we can recover using this echo process. Now, of course, you can sort of understand from this description and animation that this only works if whatever noise is causing the spread of the spin here is exactly the same noise in the other part of the sequence to have it really cancel out. Otherwise, if the noise is not static, it's changing between these two parts of the sequence, we will not get a perfect echo. And of course, this is something that other people have realized as well, and they've extended this concept of the Hahn echo to say, well, if we can put in a pi pulse, why not put 2 pi pulses, or 4, or a million? And I think probably the first people to do this were Carr and Purcell in what's called the CP sequence. So it's basically a bunch of pi pulses, and then after that, this was kind of improved by Maybaum and Gill to create the CPMG sequence. What is the difference between the CP and the CPMG sequences? It's just the phase of these pi pulses. So Carr and Purcell didn't really think about it, but they were thinking, okay, if I have this pi over 2 pulse that rotates here, we'll apply pi pulses and we'll do this, or maybe random phases or whatever. And Maybaum and Gill realized that if you change the phase of these pi pulses to be along your initial direction, so you get small rotations, and that's much, much better. And I like it a lot because Maybaum's grandson is in class with my son, so I'm super excited. Nobody else cares, but I'm excited. So you can use this type of sequence to really suppress these types of noises that are slow and effectively get a longer coherence time. The coherence time that we measure under these sequences, Hahn or CP or CPMG, are sometimes called T2 as opposed to the T2 star from Ramsey. And we can measure these T2 times as a function of the number of pi pulses that we apply in our CPMG sequence. And we can see that it does help. So we can see that a coherence time that you measure with a single Hahn echo pulse at 250 microseconds, this is just some representative sample, nothing special. If you put in 500 pulses, you can increase this by about a factor of 10, which is not bad. A follow-up experiment that did the same thing as a function of temperature actually showed that this, it's the same plot of the number of pulses in your CPMG sequences and the coherence time, T2. But here the colors are different temperatures. So this measurement showed that at room temperature, if you increase the number of pulses, at some point you don't improve anymore. Just a second. And the reason why it doesn't improve anymore is because there's an additional relaxation mechanism that blocks us. And this additional relaxation mechanism is phonons. So the phonons that we talked about previously regarding the excited state, they also couple to the ground state, not as efficiently, luckily for us, but they do couple, and they limit the coherence time of the NV spin at room temperature to a few milliseconds. And the relaxation caused by the longitudinal relaxation that's dominated by phonons is called T1 in NMR jargon. So the T1 is about 5 milliseconds, and it limits our T2. But as we cool down, and then the different colors here are different temperatures going all the way to the black here, which is liquid nitrogen, 77 Kelvin, we can see that cooling down suppresses this phononic relaxation and allows us to extend the coherence time to longer and longer times. So here it's not even at saturation with about half a second, but it just took us 2 weeks to take this data point, so we didn't go any further. There was a question?
Yeah, well, I couldn't understand. So there is basically 2 questions. So I couldn't understand how you are measuring T2, and like that already answered, like if we cannot increase the number of pi pulse So there is a certain limit. After that, we cannot increase. So how do you know that?
Yeah, so actually there's a couple of points here. First of all, in principle, you can, so here we went up to like 500. At some point we did more. Sorry, I don't have another figure for that. But in principle, you can increase the number of pulses more. There's nothing that inherently stops you. There are technical issues. The technical issues are, first of all, if you think about, this type of pi pulse idea from Hahn and how it cancels out from both sides, the kind of underlying assumption, the picture that you might have in your head is that we can do like a super fast pi pulse, delta function in time. That's of course not true. So the speed at which we can apply this rotation kind of limits us in terms of the number of pulses that we can apply, because at some point you'll want to have many, many pulses, but there will not be any time in between. So you're going into sort of like the Rabi regime, because it's actually almost a driven system. So technical limitations usually limit how long your pi pulse is and how many pulses you can stick in. In addition to that, pulses are not perfect in reality. I mean, on the screen they might be, but in reality they're not perfect. And then at some point, depending on technicalities of your system, if you add more pulses, regardless of T1 for a second, you'll just add more noise to your system, just because of your imperfect control, not because there's actual noise in the system, and that will also limit your coherence, the measured coherence. So there are technical limitations in terms of adding more pulses. In terms of how do you actually measure this coherence time, it's quite similar to the Ramsey experiment that I showed you before, and I think I have plots of this a little bit later on. But you basically can measure the coherence as a function of time. You see relaxation. It doesn't matter what the number of pulses that you applied is, but you change the time between pulses and you measure the relaxation. And from this relaxation curve, you can extract the exponential coefficient, which is the T210.
Okay, thank you.
Thanks. Other questions? Okay, so just to summarize, it's important to take into account all of the different noise mechanisms, but what this experiment shows is that we're dominated by spin noise. Actually, in this system, it was kind of a dense diamond, so we were dominated by nitrogen impurities in the lattice, so they create spin noise, which we can then suppress by applying these CPMG sequences. But at some point, phononic relaxation that causes that's called T1, that causes population relaxation of the NV spin, limits our coherence time, and these pulses that we apply don't help. Only cooling helps. Why do these CPMG pulses do not suppress the phononic relaxation? Never mind, think about it.
Hey, you're supposed to answer those
I am
questions.
supposed to answer it. I wish I knew the answer. I only ask questions that I don't know the answer to. No, so actually, it's kind of an interesting question, which I'll touch upon in a second. But remember when I told you that in the excited state, these phonons really mix the orbitals very quickly. In the ground state, these phonons have this coupling and they cause this relaxation. It's not very quick. It's on the millisecond time scale at room temperature and then even slower. But the phonons themselves, the phononic environment, couples within itself extremely quickly. It's something that we sometimes call a Markovian reservoir. It has no memory. And if it has no memory, it means that on each side of the pi pulse, no matter how many pi pulses we have, the noise will be different. So our control can never be fast enough. Our sequence of pi pulses can never be fast enough to decouple or to suppress this phononic relaxation. This is, of course, not fundamentally true. There is some time scale for the phonons, and if we could apply control faster than that, something might work. But this is in picosecond timescales. We can never do this graphically. So that's why it's a limit for us. So trying to go through a bit more kind of important aspects of these color centers, let me just mention the surface. So far, we've been talking about these defects in general. They could appear anywhere within the solid crystal. But in many cases, and specifically in this kind of like sensing scenario that I mentioned to you before, not only, but specifically in that case, we tend to want the NVs to be close to a surface so that they would be very sensitive to whatever we place on top, whatever it is that we want to measure, okay? So how close do we want them to be to the surface? As close as possible, maybe. But then apparently what happens is that as they get close to the surface, they're not only sensitive to whatever it is that we want to measure, they're also sensitive to whatever crap there is on the surface, and there always is. So noise from the surface tends to affect properties of shallow NVs that are close to the surface, and that's an issue that, I mean, even some of you are trying to actively address. I'll just mention very briefly that we've, together with Hofmann at the Technion, tried to address this as well through a very nice process of nitrogen termination with a very gentle nitrogen plasma in a system that Alon has, which is in ultra-high vacuum and allows this to be done in a very clean environment. And what we've shown was that if you take shallowly implanted samples, so in this case, to create these NVs that are close to the surface, we start with a very pristine diamond sample that has pretty much no NVs in it, and we implant with a very low energy. This was, I think, 2 keV. And what happened was that we pretty much saw nothing. So the NVs were so strongly affected by impurities and charge traps on the surface, any type of dangling bonds, any type of something not pure that's on the surface could affect these NVs. And specifically, we almost saw no fluorescence. So the fluorescence was being quenched by whatever it is on the surface. And the little bit of fluorescence that we saw didn't allow us to measure anything. We couldn't see any spin signal out of these NVs. And then when we applied this surface termination process with the nitrogen plasma, NVs showed up. So we could see them now, and we could even measure their properties. We then compared it to a different process that destroyed it, never mind. But these are the actual measurements that we've done on these NVs after termination, which we could not do before. I don't want it to go into too many details, but you can actually use them. So that their coherence properties are not great. T2 star times are, not very long, about 4 microseconds, but still usable, especially because of their close vicinity to the surface. I do want to mention something that we've tried to do recently, and it's related to a paper by Shimon Kolkowitz from a few years ago, which looked at relaxation processes of shallow NVs. These were NVs in nanodiamonds, but in any case, shallow NVs in principle. And what he showed was, if you remember, we were talking about relaxation, this process that's called T1, where, a spin 1 can go into 0 or vice versa, or -1, whatever. So all of these population changes that are dominated by phonons usually. And this is a kind of a characteristic relaxation curve. It's measured through the fluorescence, but essentially this is how a state, say 0, relaxes as a function of time. And you see this relaxation with a characteristic time scale. I don't know what it is. But you can actually, because this is not a trivial system, this is an NV with 3 spin sublevels, you can measure relaxation from different states, from 0 or -1, from +1, from 0 to 1, from 0 to -. You can measure all of these different kind of relaxation paths. And what Shimon showed was that the +-1 states for shallow NVs, you don't see this for deep NVs, relax much faster. Actually, I have this like 2 time scale thing, but they relax much faster. And what causes them to relax faster? Noise on the surface. So the phonons are there. They always couple to everything. But noise on the surface at low magnetic fields actually allows for this transition to happen efficiently. This is kind of an electrical coupling that causes this relaxation to be more efficient or faster than for the zero state. What that got us thinking was, this is an interesting scenario where this relaxation process for these specific shallow NVs is not dominated by phonons. It's dominated by, you know, those charge traps on this kind of electric noise from the surface. But this electric noise on the surface might not be very fast, maybe. Right? Remember I told you we cannot fight phonons because they're too fast. We apply pulses, doesn't help. Yeah.
Thanks. I'm confused. You say relaxation out of zero. Where does it relax to?
Plus and minus one.
Why is it called a relaxation?
The terms I think that I'm using are pretty common, but you know, names are names. Relaxation is the term that's related to population going from one state to another, versus decoherence or dephasing, which usually describes noise where you have some population. It doesn't change, but the phase gets scrambled. So you lose the coherence in a density matrix type picture. If you're familiar, it's the off diagonal elements that decay to zero. And for the relaxation, it's the diagonal elements. But these are common names, don't mean anything beyond that.
And you show the relaxation out of zero to either plus or minus one, but they're not the same. They have different. Don't they have different rates?
Yes. So what this plot shows is that when you relax out of zero, it's slower than relaxing out of plus one.
But you plot relaxation out of zero to plus one and relaxation out of zero to minus one in the same plot.
No, sorry. This was, maybe I was not clear, but it's not me, it's Shimon's paper. So this is relaxation out of zero in yellow and relaxation out of plus one in whatever this is, purple. So the relaxation from zero is governed by these rates, taking it from zero to plus or minus one. But the relaxation from plus one includes also this gamma. And apparently this gamma is fast for these shallow NVs. That's the bottom line of this talk.
What I don't understand is why you can plot the relaxation from zero to plus one and from zero to minus one in the same graph, the same color.
Oh, I don't know I just measure how fast it goes out of zero. I don't really look at where it goes. So it's just a measurement that tells you how fast the population is leaving zero.
Okay.
And similarly for plus one. Other questions? Yes.
So in your lecture, you have demonstrated that several ODMR plots and the contrast is all different. How deep can it go and why was it all different in all your graphs?
Because, materials are hard. We always see that there's a lot of variations in all of the parameters of the system, and this is where it has an Achilles heel compared to atoms or ions, which are all the same. And the surrounding environment and all of these different types of noise sources and additional strain within the lattice and so on, they can all affect various properties of the NVs. One of them is the contrast that we see in the ODMR. So I think that maybe the best contrast that people see is approximately 40% or so, but it is quite common to see contrasts that are much lower than that on the scale of 10% or even lower. This depends also on whether you're looking at a single NV versus ensembles. So there's a lot of details that I cannot go into all of them. Some of them I understand, some of them I don't. But definitely a big issue with using these systems is that they're real world solid state systems and they're not all alike.
Yeah, indeed. Thank you.
Oh, yes.
Does the contrast also depend on the depth at where you implant the NVs?
Yes. But again, not in a super clear way that I can tell you. I mean, as I just showed in the previous slide, you can be with the NVs at a specific depth, but depending on what's happening on the surface, whether it was terminated in a certain way, whether it was cleaned in a certain way, that would modify the kind of defect structure or the noise structure from the surface, and that would then modify, for example, the contrast and other properties of the NV, even if it's, even if they're producing the same data. So there are various parameters that go into this, and it's very difficult to give, a straight answer.
I guess it's also quite important how you're close to your microwave source. That's also
What? Sorry.
How you're close to your microwave source. That's also directly affecting the contrast that you have.
That's true. It depends on how you do this measurement. You can actually do a measurement in a kind of a pulsed ODMR way where you're less sensitive to the strength of but you do need to have a good control, a good high pulse rotation. But in principle, yes, all of these things, even technicalities, go into the measurement result.
Don't want to be the party pooper here, but it's 10:30 already.
You should have given me like a heads up, no?
Yeah, giving you a heads up.
Shit. So let me, I do have a little bit more to say. I promised a little bit more. So a few more minutes, yeah, okay, thank you. So I just wanted to mention here, I'll do this quickly, but I told you that we cannot stop relaxation because the phonons are too fast. Here for the ±1 states, the fast relaxation is not from phonons. It's from noise on the surface, which might be slower. So we did echo on the relaxation process, and we can see that we can extend T1 compared to the standard, let's say 0.4 microseconds we got here, to 13 microseconds. So we can actually do echo on the relaxation process in the case where the noise is not very fast. So there's no intrinsic reason why you cannot do this type of refocusing. Sometimes people call this dynamical decoupling on relaxation processes. People do this mostly on decoherence, but you can do this also on relaxation. But what do you have to do differently than CP and CPMG so that this pi pulse would work? The answer is on the slide. Can I apply the same pi pulse as in regular echo, in regular Hahn echo? Come on, guys. Pi Z, it says pi Z, exactly. I cannot rotate around X because the relaxation process is kind of an sigma X rotation. So I have to do something that's perpendicular. We apply a pi Z pulse around Z to refocus this. How is that done? Oh, more. Okay, so since I don't have much time, I just want to flash up. I talked a little bit about the hyperfine coupling. I didn't really talk about NV orientation, so I didn't want to flash this up. And the NVs inside the diamond crystal have this orientation along one of the 111 directions of the lattice. But if we have many NVs within the crystal, they could be in any of the 111 configurations, so 4 different configurations. Compound that with the hyperfine splitting, and you get a bit of a mess. And Arnie can tell you more about this during the coffee break, but you can do a lot of very nice things. You can measure this mess, but you can also, this is a plot as a function of magnetic field and the frequency, and this just shows the strength of the transitions. And these are kind of line plots at different magnetic fields as a function of frequency. But you can characterize this very carefully, but then you can also utilize it in very smart ways to perform magnetometry or other things, maybe even gyros. And maybe you'll hear more about this at HIM later on today. So this is a plot for you. So I want to sort of finish up by, you know what, I'll skip this. I just wanted to mention that there was this NV0 that I told you about at the beginning and then I forgot about completely. Unfortunately, we cannot forget about it because the optical excitation processes that we like to use for many of our experiments can also cause ionization and recombination, can cause transitions between the minus state and the 0 state and vice versa. We can study this, we can look into this. There's some interesting questions there that I don't want to go into right now, but you can find material here and in other places. But it's also something that you just have to keep in mind. in some of the experiments that you do, because sometimes these maybe unwanted charge transitions could, affect your experiment, could be problematic or whatever. So let me just quickly finish up by reminding you that at low temperature, we can create nice coherent optical couplings. This is from a paper by the Hansen group, where they actually showed this nice entanglement between two different NVs and two different systems through an optical link. And that can only be done if all of the couplings are coherent. So this was done at low temperature at about 10K. And it was done in a way, there are various ways of doing this practically. Maybe the straightforward way is to have the polarization of the emitted photons be entangled with the spin states in such a way that you can then distribute the entanglement to another defect. These are extremely difficult experiments, but they're very interesting if you think about how can we take the system in the context of coherent coupling, distributed entanglement, quantum internet, quantum computing, whatever. Use the system in that context. So these are the things that you like to keep in mind. And these things actually also remind us the downsides of NVs. If you remember, the coherent emission of the NV, the ZPL, is weak. And therefore, it's not a great system for doing these coherent optical couplings. And that also led people to look into other defects in diamond that are sometimes called group 4 defects. So they're like, this is the NV, but this is, for example, another group 4 defect where you have, which is kind of symmetric. You see two vacancies and the defect. This could be silicon, germanium, tin, lead. And they're very, very nice because their symmetric nature makes them, first of all, much more stable in terms of their optical frequency. They don't have a permanent dipole, so they're much more stable to electrical noise. If you remember this kind of line jumping around in that plot that I showed you a while ago for the NV. So these are much more stable. And also, they have a much stronger coherent optical coupling. You remember we talked, sorry, you remember we talked about the Debye-Waller factor, what percentage of light is emitted into the coherent zero phonon line. For NVs, it is bad. For these group 4 defects, it's much, much better. So people are looking into these other defects, for example, the silicon vacancy, germanium vacancy, and so on, because they have this nice advantage. Do you think that anything comes for free? No. What is the big disadvantage of these defects, all of these group 4s? Sorry? I'm sorry, I cannot hear you. You need low temperatures. Why? In this table. All of these group 4 defects do not have an orbital singlet in the ground state. They have an orbital doublet. What happens when you have an orbital doublet? Phonons mix them. And if phonons mix them, we're dead. So what you have to do to stop phonons from mixing your doublets, you have to cool down. And the silicon is annoying. You have to go to 100 millikelvins to, what determines the temperature that you have to cool down to? Bless you. Okay, quickly. I don't have time.
The energy difference between the state.
Thank you. The energy difference between these orbitals, and you can see this ground state splitting here. The bigger the ground state splitting, the higher the temperature that you can work with. Okay? So silicon vacancies have about 50 gigahertz, so very low temperature. And then as you go to heavier and heavier defects, this splitting grows and you can work at higher temperature. The lead, we don't know that much about, very few experiments, but the tin seems very, very useful, and people have been able to work with it even at around 5 Kelvin. So it's already like a regular helium cryostat, and it might be very interesting for various applications. So basically what I'm trying to tell you in this part of the talk, I'm old, I work with NVs, forget about me, you're the future. Look at other systems, okay? So other systems also means not necessarily diamond, right? So why should we stick with diamond? Diamond is nice because, it's a physicist's best friend, but it's a difficult material to work with. This is also advanced over the years, but it's still expensive, difficult to work with, and so on. If we could work with silicon, or for example, with silicon carbide, which is kind of similar to diamond, that could be an advantage. So people are looking at other material platforms as well that have their own advantages. People have been looking at die vacancies and other defects in silicon carbide. By the way, for the question about how we measure T2, this is just a measurement of T2 in die vacancies in silicon carbide. So this is just, you look at the relaxation in an echo. This is actually CPMG, with different numbers of pulses. But you just look at the relaxation as a function of time and fit it to an exponent and get the number. So people have been able to get very nice results out of these defects as well at low temperature. So this still only works, and maybe there's been also some results at room temperature. I don't remember, but please look this up if you're interested. I'll just mention briefly that when you're looking at other material platforms for useful color centers, you want perhaps materials that are easier to work with than diamond, but maybe you want materials that give you some other advantages. And an interesting direction that people have been looking at is van der Waals materials, these materials that you can exfoliate to very thin layers like graphene, or in this case, HBN. And if you have useful color centers, useful defects in these materials, then you can imagine how that could be practically beneficial. You can integrate them into other material platforms, create devices that integrate these color centers for sensing or for other couplings. So there's some potentially nice things that you can do with them, and people have been trying that. HBN, for example, hosts many different interesting color centers. For example, boron vacancies or carbon centers. People have been able to show ESR and ODMR and whatever. These are actually experiments using boron vacancies in HBN integrated with a device, in this case, a YIG, to measure magnons in this system, and also have been able to polarize the nuclear spins within the system. Like I said, nothing comes for free. HBN, for example, has a lot of nuclear spins, so the spin properties of the defects in it tend to be not so great. So people are trying to think how to work around it. And in the next part of my talk, I'll talk a little bit about polarization and how that could be useful. So I'm finishing. So now you know everything about color centers. And after the break, I'll try to tell you about some techniques about things that we can try to do with them, characterizing errors and noise as we learned, going to many body systems and polarization transfer, and I'll give you some examples of ways to do sensing. Thank you very much.